Okay, guys, so basically today we're going to do some problems, but this is some material that now they don't, I used to cover this one, but since the other sections do not cover it and they want some uniformity, I'm not going to cover it, but I'm going to mention it to you. Okay? So basically there's something called the coefficient of restitution, okay, which will go over here. Okay, coefficient of restitution. So when there's an impact, let's just think about something. Okay, what is happening? On the impact, some of the energy you are coming with or momentum, you're going to transfer it to the other object now, and you're going to lose some on the way, no? So for example, if you have a car accident, you lose energy on the what for? Deformation, so the generally will be noise, no? Then it gets heated and there is deformation, no? So you lose type of the momentum. So for example, if you think about a ball that is bouncing, depending how much is inflated, it's going to bounce back. But if the impact of the ball with the surface is perfectly, let's say, elastic, which is opposite than plastic, no? Elastic, then the ball will probably bounce back to the same height, no? So that means you haven't lost anything during the impact of the ball with the ground. The other opposite would be what? That you drop the ball and it stays right on the surface because it melts with the surface, no? That type of impact will be completely plastic. So if you think about it, the coefficient of restitution is the type of stuff that is measured. If you have some initial velocity going here, the difference, okay? What I like to do is more the other definition here. This one is like the value of the reactions before the impact divided by the reactions right after the impact. Correct? So if there is no change of the value of action reaction, this should be just equal to 1. The impact will be said to be completely elastic. No? That's the ball that bounces completely back. If now all the energy is transformed, for example, if you don't have any more reaction is whatever is. There is no more reaction, so the ball can fall back. This will be equal to 0. Okay, but obviously life is not 0 or 1; it's a middle step. So basically, you derive this equation, which basically is given in function of the velocities before the impact and after the impact. Okay, but again, we're not doing this. Basically, there's multiple problems over here. Whatever. Let's go back to the problems we're trying to solve. But what I want to say is that momentum is really used for impact. So for example, this problem over here, okay, we can maybe solve it just assuming this is completely elastic. But what will happen if the bar, you let this bar here drop about this point? So here it's going to fall just, if you want, just horizontally. But as soon as it's going to hit that, it's going to bounce back probably, and then it's going to have some motion. There's going to be translational and rotation, no? But initially, the motion of this bar will only be translation, but after the impact, it will have translation and rotation. Correct? Okay, so that's the type of problem can solve with the impulse and momentum and the angular momentum. But initially, let's just solve 1971. Okay, so do this figure. I do this figure on the paper, and then we start working on this problem. So problem 1971. So the length of the bar is 1 meter. There is a ball moving with an initial velocity, let's say VA equal to 4 meters per second. The mass of the sphere here, they say, is 2 kilograms. So the 2 kilogram sphere moving toward the right at 4 meters per second. When it strikes the end of the 5 kilograms slender bar, so let's say 0.4, let's call this one MB equal to 5 kilograms slender bar. Immediately after the impact, the sphere A is moving towards the right at 1 meters per second. So let's say VA prime prime will mean right after the impact is 1 meters per second. What is the angular velocity of the bar after the impact? So if you look at my figure, this is my figure over here. Yeah. So basically, I do the ball 2 kilograms, initial velocity VA. The bar is 5 kilograms. Initially, it's not moving. Then the velocity after the impact is 1 meters per second. The one I know will be the angular velocity of the bar after the impact. No? 1 meter per second to the left and to the right. I mean, it's going to keep moving to the right. But yeah, good question. Okay, if they don't tell you to the right. Okay, so are you ready? Okay, so if you want, I always like to do first some type of figure. So let's say, what would you have? So the first figure would be identical to what we have over there. Okay, the only thing I'm going to do is maybe call this one here MAVA. All right. One O. So VA initially, what is, maybe I'm doing too much here. What will be the initial velocity of this? 0, no? And the initial angular velocity of this one will be 0, no? Okay. So, and then let's say this will be before impact, and let's say this one will be just after impact. I'll do this figure over here. So right after impact, what you're gonna have MA here with the other velocity, V prime A, no? And then over here, we can be careful. So we're gonna have the two choices. We can have MB, V prime B, and then we might have over here I omega. Let me just call omega primes for the final as well. So any question about the figures? Do the figure make sense? If you remember, we're gonna get all the equations from the figure, no? So always kind of the same procedure. First figure, second step is what? Apply kinetic equations, work on energy. In this case will be impulse and momentum, no? Okay, so two, if we solve this problem using impulse and momentum, so let's say impulse and momentum. So again, so the impulse and momentum, this equation is a momentum equation. So when you take the moment equation, what is the first thing you need to define? When you take the moments, what is the thing you must define? What is it? About which point you take the moments, no? About which moments are we going to take the moments in this problem? Okay, so let's say taking, if you want, I'm going to be more specific, angular momentum about O. Okay, so I'm just going to write down the general equation. What is the general equation? Is R cross summation of forces dt plus summation of moments dt equal to R, oh, did I call R or S cross MV? I don't remember. The distance, did I call it S or R? R, okay. R cross MV between V initial and V final plus, what should I have now? If I do the same notation, it would be I omega between initial and final. Okay, in these problems, do we have any force?
No. Well, it's not weight, is it?
The what? Okay, you have the weight. If you have the weight, that's fine. If you want to put the weight, but the weight will be acting through which point? Point no, so we'll not be creating any moment. No? Correct? I will have moment. So you agree that all these terms over here will be 0 and 0. Yes? There is no forces. And if you want to put the reaction of the pins over here or the weight, they go through point O, no? So they don't create any moment. Yes? Okay. Just waiting for your approval. Yeah. Okay. So basically, I could rewrite this as something that will be known as the conservation of angular momentum. You could have what? MV final minus R, MV initial plus I omega final minus I omega initial equal to 0, which will give you R MV initial plus I omega initial will be equal to R MV final plus I omega final. Okay, so what name do you think we can give to that equation? Before we had a similar equation that was MV initial equal to MV final. We call that one what? Conservation of linear momentum. Now, this one, what do you think we can call it? Perfect. Conservation of angular momentum. Okay, so we're going to do as before. We're going to use that equation now with this figure here. So now, remember, we kind of discussed that a little bit at the end of the class, that we might have the same issues that we had with work energy. Let's look at the motion of the bar. What is the motion of the bar? Yeah, it doesn't matter. It doesn't matter which figure. So what is the motion of the bar? What type of motion is the bar having? Rotation. But if it's rotation, what else do we need to specify? Okay, the motion of this bar right after the impact will be rotation about point O, or it will have, if we take the moments, about point O, no? But if we take it about the CG, then you have what? Rotation and translation. Correct? Yes? Okay. So in the first case we're going to say that we take everything about point O, no? The motion of the bar is about point O, correct? All right. So let's look at this equation here. Okay, so from this equation here, from the figure, all right? From this figure here, I'm going to rewrite this equation. So initially, let me just rewrite it. We had R MV initial plus I omega initial equal to R MV final plus I omega final. And the length of the bar is Let me just call this one L, no? Just gonna use L. All right? So let's see. Initially, what is the angular momentum about point O created by the moving mass MAVA? Ready? What would that be? I mean, look at the equation. What is, so we have what? What would be R? Okay, but 1 basically would be L, no? Yes? So the arm is L. What would be the value of the force if you want? Or the momentum would be MVA, no? This one over here is going to create a moment about point O, no? Yeah? And it's going counterclockwise, so we can say it's positive. So now, is this one moving initially? No, so it's not creating as no velocity, initial or final. So at the beginning, the only thing creating an angular momentum is the ball moving at a velocity MAVA. Agreed? All right. Now, right after the impact, what is creating an angular momentum about point O? Okay, but what about the ball first? Is the ball still going to create an angular momentum? So we have MA, but this time will be V prime A velocity after the impact, no? Okay, now is where this is we can have two equations. Maybe I'm going to write them now. I'm going to write the two equations now. I'm going to solve one way, and then you have to solve the other way. Now, what about the bar? So the bar, if we say it's only rotating, we need to do what then? Take the moment of inertia just about point O, no? Okay, and this will be now omega prime, the final. Any question about that equation? Let's call that equation A. Okay? Yes.
If the bar were moving initially, would it be that equation having what plus?
You will have on the left hand stars, yes, plus an initial I omega if you want. But I mean, maybe more than that. So I can solve the problem doing this, or you could use what? So let's say initially I could say the same thing, MAVA equal to L MAV prime A. Now, what would happen if I take the moments about the CG? What would you have now? I mean, that what would be the V prime? What is the location of this? And what would be the length?
1/2
The L over 2, no? And then you have what? Mass of the bar. VB prime or V prime B, no? Plus what? ICG omega. So you could use either one of these ones, and that should give you the same answer. Equation B. So I'm going to solve with you in one case, and then I'm going to give you 5 minutes or 10 minutes to solve with the other one. So which one do you want us to do together? Using A or B? A? B? Okay, I'm going to flip this. Whatever, we're going to flip it. I mean, somebody's going to decide. One of the... Let's see, randomly. Over there. Which one do you want? A or B? Yeah. A. Okay, it will go. Okay, we decided with A. And then, so basically with these steps, 1, 2. Okay. So now in this equation over here, that's the good thing about this one. So it'll be easier. Okay, so using case A. Do you remember over here, Johnny, what is the procedure? You stop, you have one equation, no? Yeah. Using equation A instead of case A. Equation A, sorry. It's more, it's not a different cases. Equation A. So out of the equation A, how many unknowns do we have? Do we know VA? Do we know V prime A?
Yes.
The unknown is really omega prime, no?
Yeah.
So we can basically go and solve. Now, let's think a little bit ahead, okay? The next thing you have to do is solve with this one. How many unknowns are you gonna have? You know VA, you know V prime A, this will be unknown, and this will be unknown. So that means you have one equation, and you need another equation. Where are you gonna go find the other equation? Kinematics. Out of kinematics, what can you do? You can find the velocity of this point from which point? 1.0, no? Basically, it will be the same thing. Yes. For a bar is m squared over 12, but I will give you on an example the problem. So using equation A, we see we have one equation and one unknown. So what can we do? Go and solve. Okay. So basically, let me just rewrite here the equation L M sub A V A equal to L M A V prime A plus I sub O omega squared. I mean, I hold up now. You know that I'm going to give you over here ICG over bar is what? M squared over 12. Then you can move it to 2.0 using what? The upper axis center would be ICG plus what? MK squared if you want. MK squared, where K squared would be equal to what? L over 2. I'll let you do the calculation. I mean, we have done that. What should you get for this one? M squared over 3, no? Do you know what I'm talking about here? Well, we have done it multiple times, no? You move the, basically, what we're doing physically is that we're moving the I from the CG to 2.0, no? Yeah? So I'm moving the effects that happen upon the CG to 2.0. Okay, so over here, what is the only unknown that we have that we need to solve is omega prime. So we can say omega prime would equal to what? LMA. Yeah, so I can maybe just write under the form might be a little bit easier. LMA VA minus V prime A divided by, I need to be careful here, this will be ML, M sub B, L squared over 3. Okay? So, you know, I like to do it symbolically, but since you're going to be the one doing the part B, maybe numerical application. Will be what? Omega prime is equal to what? Okay, I trust you. It's 1 times what was B times 2 times VA is 4 minus 1 divided by what? 5 times 1 square divided by 3. So what is this? 1, 2, so 2. 2, 6, 6 times 3, 18. 18 over 5, whatever that is.
Yeah, that's
3.6. Yeah, that makes sense. 3 times 5, 15. No? 6 times 0.5 is 3. 15 plus 3, 18. 3.6. Okay. Using equation B. All right, let's do it together, okay? So what do we have here? We have L MAVA equal to L MA V prime A plus, do you understand the L over 2? If not, this is the time to ask questions. The L over 2 is because MV V prime B is located at the center of the bar, no? It's located at the CG. Yeah, so this is L over 2. All right, plus ICG V prime B. So here what happened? We have one equation.
Wait. Then the last one will be.
Omega, sorry. Yes, omega prime. I was thinking too much about the omega prime. So two unknowns, which the unknowns would be what? V prime B and omega prime, no? So you see, same procedure. 1, 2. Where do we go get the additional equation? Yes.
So you want to count what we given with the first equation.
But that's what we're trying. We're solving the same problem now using this equation instead of this one. Okay, we're doing exactly the same thing. So we need to find the additional equation. Where are we going to go get the additional equation? Kinematics, okay? So I know, so the problem is over here. So let's say we use the other one. So let's say from kinematics, we can kind of see one of our steps would be kinematics to find additional equation. So what can we write down over here? We can find the velocity here of V prime B from where? From point O, so we find V. So let's call this one V prime B. Will be equal to what? VO plus omega prime final cross S of, yeah, okay. Let's say this is B, okay. CG will be over here if you want. B with respect to O. So what is the velocity of O? 0, so this will give you IJK 0, 0 omega, and what would that be? Position of B with respect to O will be positive or negative L over 2? Negative L over 2. So this will give you that B prime B will be equal to what? L omega 2 omega prime, no? So let's say that one. That one. So now we have what? The two equations. So we can say substituting into equation B. What do we have? We have L MAVA equal to L MAV prime A plus L over 2 MB V prime B plus ICG omega prime. Remember, this is the time to ask as many questions as you want. Don't wait to get lost. Okay, so now what is the only thing I'm going to do? I'm going to replace this V prime B by what? L over 2 omega. So basically, this means I'm going to get L MAVA equal to L MAV prime A plus what? L over 2 M sub B times L over 2 omega prime plus ICG Now, if you know the product theorem, everything's gonna make a lot of sense. Omega prime. So let me just rewrite this as LMA equal what? VA minus V prime A will be equal to what? Omega prime times what? ICG plus MB of L over 2 square. Correct? And what is this? I sub O. So we get exactly the same thing as before, no? See, I like to do numerically because you see what's happening. So this will give you that omega prime equal to what? L M A V A minus V prime A divided by I sub O, which is what? L M A V A minus V prime A divided by the MB L square over 3. As previously, no? Yes.
On the exam, which asked us to do both ways, or just saying you want to basically just solve that.
Oh, I'll give you the choice. I'll give you a choice. That would be your choice, okay? But I just want to show you here that because I think it is both ways that gives you good understanding about what's happening, no? That's the only reason I do it. So we can do more examples. Rather, we are limited here because of the impact type of run we can do. Oh, let's do this one here then, I guess. E is equal to 0. So 1966. Is that for this one? Yeah. Okay, that's fine. But then what's going to happen here? Okay, let's look at it. 1966. I don't fully understand the problem. But maybe as I write it down, I get some understanding. So let's see, the 4 kilograms bar is released from rest in a horizontal position above the fixed projection at A. Okay. The distance B is 0.35. Okay, I see it now. The impact of the bar with the projection is plastic. That is, the coefficient distribution of the impact is 0. What is the bar angular velocity immediately after the impact? Okay. So the length of this bar will be, let's say, L equal 1 meter. It's gonna hit a pin connected at H equals 0.2 meters. And the distance over here, B, is 0.35. So what do they have? Plastic. Impact. Sine omega prime. I don't think this one makes too much sense, but it is what it is, okay? Because basically what is it saying is that it's saying that the bar is going to adhere to the pin, which is like, okay.
If it's plastic, would it adhere or would it bounce?
I mean, if you put 0, it's gonna get absorbed. I mean, it might bounce. What happens is that it's gonna get absorbed by the pin and then it's gonna start rotating. So it means like if this was then just being attached to that point, I would start rotating about that point. Okay. So, all right. So basically, again, you want me to give you about 10 minutes and you try to do it? Okay. I'll give you 10 minutes, try to do it. Basically, do the same thing as we did before, okay? Don't overthink. All right, let me show the figure if I did not resume the recording for this problem. 1966, at least you have it on the video. Okay, so I'm looking for different type of problems to solve. I don't see them over here. So let's see somewhere before. Oh, I think I saw what I wanted. There we go, mass flow. Those are one-to-one. Mass flows. Here we go. So basically, I mean, the typical example, probably we'll do this one later on, is that when you have a rocket that is moving, the mass of the rocket is going to change because it's burning fuel, no? Okay. But this a problem, and then this would be flows. But this one that I like, John, is like a chain that you move out of the floor. That one, John, is a good problem for understanding. There we go. I think it's that one, this type of problem here. Okay, so I'm going to start stating this problem and then let's see we have time to solve it for today, okay? So let's look at what, 16, 114. So you kind of do the figure, I do the figure, we discuss it a little bit. So 16, 114. Suppose that you grasp the end of the chain that weighs 3 pounds per foot. Okay. I lift it straight up to the floor at a constant speed. So this is important. V equals to 2 feet per second. Is constant. Determine the upward force V you must exert as a function of the height S. How much work do you do in lifting the top of the chain to S equal 4 feet? Okay, so let's see. I do a chain over here. Okay, so really here what it comes is that what is the real definition of Newton's second law? Because
You're asking for the definition?
I mean, maybe you know what is. I mean, in physics, what was the definition they give you for? That is the definition they give in physics. But so basically, what do we in this previous chapter? We saw what that. Let's just call it P equal mv. Let's call it P over here. What is the physical meaning of this expression? This is a linear element. I mean, I'm not. No, don't complicate stuff. Okay. All right. So maybe I'm going to do some little bit of kind of small derivation. So the real definition of this is what? Summation of forces equals to what? Somebody said dp dt. This is what you learn in physics. So is this correct? Hopefully it is, no? But now you will see why. So basically this will be equal to what? D dt of what? Of mv. Correct? Now this will be equal to what? So this will mean that summation of forces will also be equal to what? Will be equal to dm dt. Thank you. Will be equal to dm dt times v plus m dv dt. The derivative of u v prime is equal to what? U prime v plus u v prime, no? Okay, so this is the real definition. If you think about it, this is actually the one we're going to use. But let's see. For the case, which is not a solution of this problem, okay? For this problem, we need to use this one. But for the case that m is constant, then what happened? dm dt equal to 0, and then what do you have? Summation of forces equals to what? M dv dt, and what is dv dt? Is the acceleration. So really, when you say summation of forces equals to ma, what is the stuff that you're assuming? Is that you're assuming with the system that the mass is constant. But if you look at the real definition, really, this is more accurate, no? So for this type of problem, since the mass is changing, which form of the Newton's equation are we going to have to use? This one over here, no? Okay. So for the present, so for this problem, let us use the form summation of forces equal to dm dt times v plus m dv dt. So I don't know if I want to solve it now because I want to solve it in detail, but maybe I'll do one more step. What did they tell you in this problem about the velocity? So what would that mean about this term? B is constant, so all this term is equal to 0, no? Yeah. So this will give you what? Summation of forces equal to dm dt times v I mean, we can almost solve it very quick, but whatever you want. Now, what would be the value of this force here? What would be the value of the weight? Okay, and G But mg is changing because as you move the bar up, that gives us that the mass is probably. So basically, what is the equation R is W is equal to mg. So really, this expression should be equal to what? This would be proportional to what? W times what are the units here? Per foot, no? So WS, because that way the more you lift it, the more it's going to weigh, no? You want, we can almost solve this. I'm going to write one more thing and then I'll let you think about it. Now, let's see dm dt. We don't know dm dt, no? We know dm ds. This is dm ds, no? Yes, this is the force per unit mass. So here we know. So how could we eliminate the time over here? What did we do previously? Do you remember? Kind of the same thing, yeah. So what could we do? We could rewrite what? dm divided by what?
Yeah.
Okay, ds.
Yes.
And then what do we need to do?
Yes.
ds dt. And what is ds dt? Velocity. So really dm dt is equal to what? Velocity dm ds. You want me to finish it or you want us to finish it next time?
It's pretty simple.
Yeah, because basically this is what you know, W equal mg. So m will be just, this will be equal to V over G dw ds, that we know this will be equal to whatever, no? Because m will be W over G. So what was the question of this problem? I forgot now. Determine how much, no, determine the upward force, F. Okay. Okay, so I forgot here, okay. All right, so we have this, we have here the force. So basically now, I mean, I'm gonna do it, but we do the second part next time, or we restart it next time, okay. Then this will give us what? Now, if we use the summation of forces equal to dm dtv, what do we get? We get the force F minus WS from the figure will be equal to what? dm dtv, so that forget F minus WS will be equal to dm, and we do it ds dt times v. What is ds dt? Is v. We're going to get that F equal to weight times S equal. Yeah, sorry, I'm doing it too fast. I know now. We will start it next time, okay? Or we do a similar problem. And this will be now what the dm ds we say that was equal to so was dw ds plus this will be 1 over g this squared. Okay, let me stop it over here. But I mean, here the thing I wanted to get today, do you kind of follow more idea the process? All right, so next class I'm going to do this problem, and next week what I'm going to do is that I'm probably gonna give you. I want to put on the page some problems that I want you to work on, and then in class, you're gonna ask me a question about the problems. But I'm not gonna solve them. I just want you to work on them, okay?